Was that a jail cell?
Can you all hear me? Yes? Okay. Can one of you try talking? I'm having a little bit of trouble with my audio. Just want to make sure.
Hello.
Yep, I can hear you. Thanks, Coleman. These are the exam results here. So you can look at those. We'll let other people jump in here. I was in a faculty meeting on Friday and everybody had these cool backgrounds of like they're in some exotic location with a beach in the background and, you know, like off of the back porch of a mansion and all this stuff. And so I decided to go with a little prison cell instead. I forgot I had put that in, so I guess I'll just stick with it today. All right, well, the exam, the grades were good. The average on the exam was an 81.7. If you look at the grades from exam 1, 2, and 3, exam 1 has been the lowest, and exam 2 went up to an 83, and then it dropped a little bit on this exam. But the more important number is the standard deviation is down to 17, which means that the class is more grouped together in terms of the grades. They aren't spread out as much. And you can see that in the chart, the gray bar here. You can see we've got A's, B's, C's, D's, and F's, where if you look at like exam 1, we had, that's the blue bar, we had like a couple of A's, lots of B's, a couple of C's, lots of D's, lots of F's. So now that people are more, I guess, doing the same, we have a more, I guess, standard deviation that's more likely, that not more common is what I meant to say, more common in a class like this. So that's good. Any questions before we begin today's stuff? Okay, we are going to meet today. We're going to meet on Wednesday also. I understand some people may travel and, you know, not be here. I'll record the lecture and post it. Just know that I am going to be here on Wednesday. So, okay, let's get down to business. We are going to continue. Last class, I had started talking about this weird sum, and I told you I would finish that off. I'm going to finish at the end of class if we have some time. But I want to start out with a new definition. And the definition, now we're still in 8.4 here, okay? So we are talking, or actually we are starting 8.4. I don't think we got into 8.4 last time. So this is just other tests. So we still have more tests to talk about on our formula sheet. So first I need to define something called an alternating series. So an alternating series is any series that either has -1 to the n times something, or you could have -1 to the n+1 times something. So let me write out what each of these would look like. If we were to write this first one out, if n is 1, we do -1 to the 1, that gives us a negative number. And then whatever a sub 1 is, so a sub 1, and then the next one will be a plus, and then a sub 2, and then minus a sub 3, and then plus a sub 4, then minus a sub 5, plus ... So it alternates. And we've talked about alternating sequences before. Now we have the idea of an alternating series where we're adding things up, but they're switching from positives to negatives back and forth, okay? Alternating, right? The other one, the only difference between the first version and the second version is that the first number here, we start with plus, and then it goes minus, then plus, then minus, then plus, and then so on and so forth. So it really doesn't matter how the alternating takes place, whether or not it starts positive or negative, it doesn't matter as long as it switches back and forth. Now we have to be careful, okay, careful. Because if we take something like this and do it in red, this is a specific example, sine of n. So sine of n, it may look like that's an alternating series because we know that sine jumps back and forth between, you know, it goes between -1 and 1, right? But the issue we run into with that one, let me see here. Let me put it in here. Okay, so if we look at sine of n, okay, ignore the red. The red is the sine function, but the black dots represent the sequence, right? So if I plug in n equals 1, I'm going to get some number here, and then 2, and then 3. See, notice these are all positive, and then it becomes negative for a little while, and then positive, and then negative again, and then positive, but it's not switching each time. Do y'all see that? It's not every other one is switching signs. So the sign is not, the sign would not be an alternating series. Yeah, okay. So I hope that makes sense. All right, so the question becomes, if you have an alternating series, is there a test we can do to determine its convergence or divergence? So now that we know kind of what an alternating series is, let's discuss what's called the alternating series test. And of all the tests that we've talked about, I'm gonna abbreviate this AST from here on out. Of all the tests that we've talked about, this one is one of the easier ones. Okay, like we've talked, let me bring up the formula sheet. In the formulas that we've looked at, well, P series is pretty easy because we can just look at the power and determine convergence or divergence. Integral test, that took some work. Comparison test, that took a lot of thought, right? Because you had to find something to compare it to. Let's see, we haven't done ratio tests, so here's the alternating series test right here. So of all the tests, this one is one of our easier ones, and you'll see once I actually run through this. So the alternating series test says this: given, okay, if we're given a series that alternates, so it's raised to the n, or this could be also n plus 1, as long as it alternates, doesn't matter how it's alternating, and then times some sequence, right? So the important thing to notice here is that this a sub n here is the sequence. The -1 out front to the n or n plus 1 is just creating the alternating part, right? So we will consider this part in yellow to be the positive part of the series. This is the only thing that impacts the sign right here. So if we're given this, then we just have to check two things. If one, a sub n is decreasing, which by the way means that a sub n is bigger than a sub n plus 1. That's what that means. And 2, the limit as n goes to infinity of a sub n goes to 0, then the conclusion is that the original series converges. So this is a little tricky because you know how I've been trying to drill into your heads that if you do this test, that test right there, and you get 0, it's inconclusive. I've been trying to tell you that for a while now. If someone gives you a series and you just take the limit of the sequence and get 0, that's the pregnancy test, and that would basically fail, right? But if it's an alternating series and that goes to 0, along with this other condition that it's a decreasing sequence, then you can say it converges. But this only works for alternating series though, all right? So it's a pretty straightforward test. Let's go ahead and run through an example. And I'm going to give you kind of the cleanest example that we can come up with, which would be something like this. Right there. So let's write out this series first. This is equal to, if we plug in 1, we're going to start with a negative. So we're going to get -1/1 plus, now we plug in 2, we're going to get a positive on top. And then that'll be over 2. And the next one will be plus. Now we get a -1 on top. And then plus, now we get a +1 on top. And then now we get a -1 on top. And it keeps going, right? That makes sense? This should, if you remember, this looks a lot like this series, 1/n. This series is 1 plus 1/2 plus 1/3 plus 1/4, right? That was the harmonic series. And we know that diverges, right? This is almost a harmonic series, isn't it? Almost, except we're going to have some things that are going to be subtracting in here, right? We have a negative, then a positive, then we're taking some more away, and then we're adding a little bit, and then taking more away, and then adding a little bit, right? So it's very much like a harmonic, but we're subtracting. So let's see, does this converge or not? So since it's an alternating series, I'm going to run the alternating series test. And the first thing I'm going to do is ask myself, is A sub n decreasing? Now we have 2 ways of showing this, right? One way to show it is to just show the inequality is true, right? And the other one is to do the derivative and show that the derivative is negative. Those were the 2 ways to show that a sequence is decreasing. Now, the important thing also is that the thing that we're looking at, the A sub n, this thing, is the positive part of the sequence. So, or yeah, positive part, which is this n without that -1 to the n on top. So in other words, we have to look at this maybe as like -1 to the n times 1/n. There we go. If we look at it that, we just kind of peel that 1/n off to the outside. This is our A sub n. Is that clear to everyone? The 1/n here is the part that we're going to be looking that's decreasing, and that's also the part we're going to take the limit of. Now, is it decreasing? Well, let's try and show this. We want to show that A sub n is bigger than A sub n plus 1. And I think if we just plug in n and then plug in n plus 1, I think we can all agree that that's true, because this denominator is bigger than that denominator, so this fraction should be smaller than that one. Is that okay? We could also cross multiply and stuff, but let's just say we're good. And then the second part is to take the limit as n goes to infinity of 1/n, and that's 0, check. So both conditions are met, which means, therefore, this series, this alternating series converges. What do y'all think? That's a pretty straightforward test, yes? As long as you can show those 2 things, you're in business. Okay, let's do another example. Let's do, are there any questions?
No, sir.
Okay, good. Alex, you sent me an email, didn't you? Did you send me an email about tests, about the test? About grades? No?
I can't fully remember.
Okay. Thought someone did. I'll just state briefly about the grades. So I know I talked to at least one student, I don't remember who it was, and I apologize, about how if you did really bad on the first exam, that maybe there would be a way that towards the end, we would replace your, your lowest exam with your best exam, like drop one of your lowest and replace it with one of your good grades. I do like that idea. However, I don't want to do that until like after the final. So I don't want, if you had a bad exam 1 grade, I want you to go into the final thinking that that grade is going to stay. I don't want you to be counting on something else to raise your grade. So I want to see the final exam grades be good. Do you know what I'm saying? Like if I replace your lowest with like exam 3, if that's your best, then it's going to inflate your grade and maybe it's going to make you study less or feel like you don't have to try as hard on the final. I'm going to be less likely to want to change a grade or replace a grade if your final exam is like really poor. So anyway, we'll cross that bridge when we get to it, but just know that, you know, if you do well on the final, well meaning not a 30, then I'm going to be open to that idea. Okay.
Okay, that makes sense. Yes. Thank you.
Okay. All right. So now, here we go. We have this series. It is alternating. As soon as you see alternating, I mean, that should be where you just go to the alternating series test. Just go to it. I mean, it's there. It's pretty easy to run the test. So maybe it's worth it for us to write out, just to split it up so we can see the alternating parts separated from the rest of it. That way we can identify the A sub n. Okay, so that in yellow is the A sub n that we're going to be looking at. All right, so here we go. First thing we need to show, we want to show that it's decreasing, so we want to show A sub n is bigger than A sub n plus 1. Or we can take the derivative of this, right? I don't really feel like doing a derivative. I don't feel like it. We could, but it would be a quotient rule. So let me just try the inequality first. If I replace all, that's on the next one, sorry. If I replace all my n's with n plus 1s, then is that true? I don't know. I mean, you could say that this denominator is bigger than that denominator, but the problem is the numerator is bigger also. So it's not as obvious that this is, I mean, it may seem obvious to you that it is, but I wouldn't say that we've proven that it is. Also, I saw in some people's tests that what they were doing to show that this was true was they were just plugging in like n equals 1, n equals 2, n equals 3, n equals 4, and just showing it was true. You can't do that. And the reason is it may do something for the first 100 terms. It may act a certain way. It's what happens at the end that matters. So you may be misled to believe it's doing something it's not if you just check a couple of values. So yeah, so you know what? Maybe I will do the derivative. So I'm going to look at this. I'm going to scratch this because I don't know, maybe I don't want to do that. So I'm going to look at this and I'm going to try and take its derivative and show that the derivative of that would be negative. Okay, so I want to show that the derivative of this is negative. So I'm not switching it to a function of x. I hope everyone's okay with that. Like to take derivatives, this should be a function of x, not n, because you know it's a bunch of dots. But in math, we actually have a term for this. This is not important. We say this a lot. Mathematicians say this a lot. Without loss of generality, which just basically means that, look, we're generalizing even though, you know, we shouldn't, like, we're not losing anything here. So we're not technically going through and switching it to a function of x, but we're not losing anything here by doing it. We know we could do that and come back to this. So, all right, so we're just going to do it. All right, so I'm going to do quotient rule. So derivative of the top times the bottom minus, now the derivative of the bottom is a little messy because it's a square root. So derivative of a square root is 1 over 2 times that square root times chain rule, the derivative of what's inside, which is 3n squared, but then times the top, and then all of that over the bottom squared. And when I square the bottom, I just get n cubed plus 2. Okay, so I need to somehow show that this is negative, right? I need to show this is negative. Now, the bottom, I'm going to completely ignore. And the reason I'm not going to talk about the bottom at all is because I know that that's positive, right? So whatever this turns out to be up here, if I divide by a positive, it's still the same value. So if everything up here turns out positive, dividing it by positive would still be positive. And if all this turns out to be negative, dividing it by positive would still be positive. I mean, sorry, would still be negative. So I really don't even need to look at the bottom. I just need to figure out what's happening here. So let me clean that up. You just let me know if you have a question on this. Let me see here. This is going to be 3n cubed over 2 square root of n cubed plus 2, like that. What do you think I'm going to do next? Anyone have an idea?
Subtract.
Try to cancel out the
n cube, one of the n cube plus 2.
So how can I do that? Because right now I'm just trying to figure out, this is just an expression. I don't have an equation, so I can't really do anything to like both sides.
Try to get the LCD or something.
Yeah, let's just get a common denominator. Let's put these two fractions together. So what I'll do is I'll have to take this one and multiply by 2 root n cubed plus 2, and then 2 root n cubed plus 2 there on top. And the good news is when I do the top one, the n cubed plus 2, the roots go away. So I'm going to be left with a 2 up there, and then an n cubed plus 2. And then I still have on the other fraction the minus 3n cubed. And then all of that over the common denominator. What can you tell me about the denominator, though? This should always be what?
Rationalize.
We could. That's more algebra than I feel like doing, though. Tell me in terms of signs, what must the denominator always be? N cubed
Positive.
plus 2. Positive, right, Peggy? All right. So no matter what, as long as n is 1, 2, 3, 4, then this should always be positive. So again, I'm going to ignore it and just focus on the numerator. Okay, so this would be 2n cubed plus 4 minus 3n cubed. All right, distribute the 2, and that turns out to be 4 minus n cubed. Okay, is this always less than 0? Always. Not always, right? When n is 1, it's not true. But once n becomes 2 or 3 or 4, this will be true. So this is true eventually, and I've used this word several times now. That's what we need it to do. It doesn't have to be true all the time. It just has to be true eventually and then hold steady the rest of the way. In fact, I can say it is true when n is bigger than 1, right? As long as n is bigger than 1, then this is a true statement. Now, this is a little misleading because when you look at the alternating series test, I've never liked this. They're saying that this has to be true for every k. Do y'all see that? And this is actually not right. I always just come in here and change this to eventually. And that's true there, and it's true up in the integral test. Where was the integral test? Yeah, when we say in the integral test that it has to be decreasing, the same thing. It's just eventually has to be decreasing, not always. So I'm not sure why it's like that in the formula sheet because it's a little misleading. You know what? I'll leave that there. Okay. So back to this. So that was a little tough to show, the first part, but let's do the second one now. The second thing I have to show is what the limit as n goes to infinity of the original thing is. And that gives us infinity over infinity. So you could do L'Hopital, right? You could do L'Hopital. I just have a feeling L'Hopital is going to get really bad. And this also happened on your test. I saw several people that had on the first problem, it was number 6, I think, where you had to show whether or not a sequence converged or diverged. So a lot of people who are trying to use L'Hopital on something that just got uglier and uglier and uglier every time you applied L'Hopital's rule. So the trick here is to multiply the top and bottom here by the square root of 1 over n cubed. Square root of 1 over n cubed. And the reason why this works is because now on the bottom, let's do the denominator first. When I put these two square roots together, it becomes one big square root. And then this 1 over n cubed distributes through to each of those. That's why I picked 1 over n cubed. And it's going to turn this n cubed into a 1. And then it's going to turn the 2 into a 2 over n cubed. And then on the top, there's different ways you can do this when you put these together. But one thing I would do is I would rewrite this maybe as 1 over n to the 3 halves, something like that. That's the same thing. I take the square root on the top and bottom. And then the square root of 1 is 1. And the square root of n cubed is n to the 3 halves. And that gives me on the top n over n to the 3 halves, which really means 1 over n to the half. So that's just properties of exponents. Now let n go to infinity. And you get a fixed number over infinity, so that goes to 0. And on the bottom, fixed over infinity goes to 0, and then you have plus 1, square root of 1 is 1, so you get 0 over 1, which is 0. So it works. Do you all want me to run through L'Hopital and show why L'Hopital is not going to be worth your time? Or no, I see people shaking their heads no. Okay. All right, there we go. So what's our conclusion? Therefore, the original series converges, right?
Yes, sir.
Okay. Now, just out of curiosity, what would have happened? What would have happened if this right here, step 1, when we tried to show that it was decreasing? What if we came up and determined that, you know what, it's not decreasing, it's increasing? What would that mean?
It fails and we have to do another test.
Very good. The test fails. This is, again, one of those situations where you would not say, oh, since the test didn't work, it's divergent, right? You don't draw that other conclusion. You just say the test doesn't work. Okay, very good. Okay, now we have some more definitions to get in place. So we have this very strange definition. I think it's strange. It's called absolute convergence. And I'll tell you why I think it's strange. Hopefully you'll agree with me. Absolute convergence. All right, so let me define what absolute convergence is. If we're given any series, okay? This is not alternating, okay? This is just any series. If we're given a series, then we say that that series, notice I'm not putting n equals 1 to infinity on these anymore. That's pretty common practice, that if you don't put it there, it's understood that it's n equals 1 to infinity, all right? And I believe your formula sheet does that also. It's not, I guess you could say they're being lazy, I don't know. See, notice how it doesn't have it, right? The only one that does is the geometric, and it's important because on the geometric, it has to be perfectly in this form for you to be able to conclude that the sum is this. So that's why that one has n equals 1. And then also on this one. And on this one also, because on the integral test, you have to start from 1 to infinity when you do your integral. But all the other ones, it's just generally stated that you have a series. All right, so if we're given a series, right, we're given the series, we say that that series is absolutely convergent if this series converges. All right. So the series in yellow is what we're given. What we're going to do to talk about whether or not it's absolutely convergent or not is we're going to take a new series which has the absolute value of what's in there. And we're going to look at that series. If that series converges, right? If this one converges, then we will say the yellow one is absolutely convergent. That's just a definition. So let's do an example. Okay, let's take this one. Yeah. Okay, is this absolutely, I'm just going to put abs converge. Is that absolutely convergent? Well, what do we need to do? We need to look at a new series, right? Which is the series that has the absolute value of that series, of the sequence, right? And when we take the absolute value, the -1 on top doesn't matter anymore, right? Because no matter what it turns out to be, you're going to take the absolute value of it, which is going to spit out a 1 on top. So we just have 1 over n cubed. And who's going to tell me what that one does? And why? Does that series right there converge or diverge?
Converge,
Why?
because the denominator is getting infinitely large, and that'll just become 0.
Careful, Christian.
P series.
It's a P series. It's a P series. So remember, Christian, we can't focus on what this is doing, right? Because if that thing goes to 0, we know nothing. Unless we're doing the alternating series test, and then it could tell us something. But if we're just looking at a series in general, right? This going to 0 tells us nothing. But we can recognize that it is a P series, right? It's 1 over n to the P, where P is 3. Right? This is a P series. I should state that. It's a P series. P is 3, which is greater than 1. And what happens to P series when you have a power greater than 1? You get convergence, right? So do we all agree that this thing converges? Yes? And so if this converges, what can we say about this one? Careful. What can we say about that one?
The original series is absolutely convergent.
Right. It's absolutely convergent. That's what we can say. Therefore, that series is absolutely convergent.
I have a quick question, sir.
Yeah.
Just going back to when you were finding the absolute value of it, why did you get rid of the power of the n in the numerator?
Okay, so like on this step right here, if I kind of left this step out, but this is what we would have. The next step, we do the absolute value of -1 to the n on top, and then the absolute value of n cubed on the bottom. Okay? Now, no matter what I plug in for n, this is either going to turn out to be 1 or -1, right? And then I'm going to take the absolute value. So it's really just going to be a 1 on top, right?
Mm-hmm.
And then on the bottom, n is a positive number, right? N is either 1 or 2 or 3 or 4. So I know that the absolute value doesn't matter because it's going to be a positive number to begin with. So it's just going to stay n cubed. Does that help?
Yeah, thank you.
Uh-huh. All right, so I have a question. Okay, this series here is absolutely convergent, right? Is it convergent though? Is this a convergent series? It's absolutely convergent, but is it convergent? How would we check to see if this one is convergent? If I gave you this series and asked you, hey, does this one converge? What would you check? Or what would you do?
Alternating series.
The
test?
Yeah, you'd probably run the
series.
alternating series test, right? And if we did that, it would actually be pretty easy to do to show that that actually converges. All right. So this begs the question: does absolute convergence mean that you can say that the original series also converges? Seems reasonable to think that, right? Well, good for us. There's a theorem. And here's what the theorem says. If you have a series, if this series is absolutely convergent, then this series itself is convergent. So what's nice about this is that if you have a series that alternates, what you can do is you can take the absolute value of it, and if it converges, the absolute value like we did in red, if that converges, then the original series is absolutely convergent. And the theorem says if it's absolutely convergent, then it has to be convergent. And that is on your formula sheets, okay? It's the last one. So it's saying here that if you're given this, right? If you're given this, then if the sum of the absolute value converges, then the original one converged. Okay. Now let's do another one.
Professor, if it diverges, do we just run a different test or?
That's right. If it diverges, we'd have to run a different test. I'm going to give you an example actually in a minute. It's actually going to be a pretty interesting example. All right, so look, let's do this one. What if you had this? Another example. What if you had sum n equals 1 to infinity? Let's say you had sine of n over the square root of n plus 1 to the third. All right. This is not an alternating series, right? This is not alternating. I just explained to you a second ago that sine n does not behave like -1 to the n does. Now, do you agree that this is going to give us some positives and negatives though? Like sometimes sine of n will be positive, sometimes it won't. In fact, I can graph this for us. Sine n over the square root of, what was it, n plus 1 raised to the third. Whoa, okay, that's pretty cool looking. So there's the first 25 points in the sequence. So I've got some positives, and then I've got some negatives, and then positives, and then negatives, and positives, and negatives, right? And we're adding all these up, but it's not alternating, not jumping back and forth. Let me show you something. I'm gonna change the top to -1 to the n, just so you can see. Whoa, what happened? Oh, there we go. So there, I just changed the top from sine n to -1 to the n, and now this is a truly alternating, right? It's negative, positive, negative, positive, negative, positive, negative, positive, right? So it's true alternating. That's not what we have though, right? So we cannot use the alternating series test here. Do you all see that? We can't. But what we can do is we can look at the absolute value of this, right? So let's look at the absolute value of this. If I look at the absolute value of this, I only have to take the absolute value of the top. And the reason I don't have to take the absolute value of the bottom is because I know n plus 1 cubed square root, I know that that's a positive number, right? Okay, so this right here, from here to here, we're taking the sum of the absolute value. if we can show that this converges, right? If we can show that this converges, then we will be able, that by the theorem, we will show that this converges, right? But how do we show this converges? Anyone have an idea here?
Would it be okay to kind of use like, I don't know, just like what my knowledge of algebra is to kind of figure it out?
I'm not sure what you mean.
So what I mean is like the absolute value of the sign, it's like that means it can't be negative, but sign never really goes higher than the value of 1, so it would be fixed. So it'd be like that fixed number over something that's going to infinity because it's a square root, but it's positive.
Mhm.
So it'd be 1 over infinity, which I think that means it converges, or am I just remembering that wrong?
No, you're right. But what you're saying is that the sequence converges,
Yes.
right? Which is basically you doing the nth term test here. You're doing this and you're getting 0, which means it's inconclusive,
Hmm.
right? So I agree with you, Peggy, that this right here, if we look at just this, I agree that that goes to 0 because it's essentially a fixed or bounded number over infinity. But the sequence going to 0 tells us nothing, right? Nothing. Do y'all see? This is obviously confusing, right? I mean, this is something that, what, last class I started with that true and false question, right? I said, if that thing goes to 0, then it converges, true or false. And we said false, right? And I say this repeatedly, right? It still confuses people. I understand that. That's why I keep on just like saying it over and over and over. I don't want y'all to get to the test and then say, oh, that goes to 0, this converges, you're done, because then I have to take off a lot of points, right? Because you have done exactly what you can't do. So I want you to make the mistakes here. That's where we learn, right? All right, so we can't, but Peggy, you were onto something though. You said this looks a lot like, this would be like worst case scenario, like 1 over this, right?
Yeah.
Okay.
It'd be like 1 over that value, and then the denominator just slowly just gets bigger because it's positive.
Mm-hmm. You know?
I don't know, I just don't remember because I know we did something like this. But to me, it reminds me of the 1 over n because it just like gets smaller because it's like the denominator gets bigger.
Mm-hmm.
Would we
I
do
don't know.
a P series?
It's not a P series because we don't have a 1 on the top. But
Can we do the ratio test?
we haven't done the ratio test yet.
Oh, my bad.
The integral?
Do you want to integrate it? I don't want to integrate it. You're getting there. How about we compare it to something? Why don't we compare it to something? Now look, the comparison test, the reason why we didn't start the problem with the comparison test, the reason I didn't even start it is because in the comparison test, we have these conditions that whatever the sequences are in here, these have to be positive for you to run a comparison test, right? These things have to be positive. Then you have these choices of what to do. For us, the original series was not always positive. Sometimes this stuff was negative, sometimes it was positive. So by taking the absolute value, now we know that everything here should be positive, right? And now I can run a comparison. Now, what would I want to compare it to? This is where I was saying, Peggy, and someone else said it too. This looks a lot like 1 over what? Just think about if we're saying that's kind of like 1, and then maybe this +1 really doesn't make that big of a difference. This would be the square root of n to the 3rd. What would the square root of n to the 3rd be?
N to the 3/2.
n to the 3 halves, right? So you remember, we have to come up with a thing to compare it to. We have to come up with that. So I think this is a good candidate, right? This is a good candidate to try. And we know this is p equals 3 halves, which is bigger than 1. We know that this converges, right? So we're going to try and compare this series here to this series, and we know it's a convergent series. So now here's where we have 2 choices. Can someone tell me what my 2 choices are? Once we've figured out something to compare it to? I
Is
can
it that
either,
it stays above or below?
yeah, I can either do this. Which one do I do? Do I do part 1 or 2? Which one am I looking at? 1 or 2 here? The
One.
thing that we're comparing it to converges, doesn't it?
That'd be
So
one.
we can either do this, right? We are not doing this because the thing we're comparing to it to does not diverge, right? So we don't do that. So we can either do the blue, or we learned at the end of class last time that there's another way we can do this by doing the limit comparison test. We can do this limit of the ratio of the sequences and hope to get a positive answer, positive real number. So these are our 2 options, the blue or the green. What do y'all want to do? Do y'all want to do a limit, or do y'all want to do the blue one? Which means we need to show this inequality is true. I don't care.
The limit?
You want to try the limit? Okay, let's do the limit. See what happens. Okay, so what we're going to do now is we are going to take the limit as n goes to infinity of which one over which one. So it actually doesn't matter. You can get this backwards on accident, but the formula says a sub n over b sub n. All right. So that's what I'm gonna do. So I'm gonna take a sub n. Now this is a sub n, and this one is b sub n. All right. So here we go. I'm gonna take absolute value of sine of n over square root of n plus 1 to the 3rd over 1 over, I'm going to rewrite the other one as the square root of n cubed, even though it's the same thing. So I need to figure out what this limit is. And then this is limit as n goes to infinity. Okay, now I'm going to just flip this. So this can be sine of n over square root of n plus 1 cubed times square root of n cubed over 1. So I just flip that fraction up, and I'm going to make that go limit n goes to infinity. I'm going to go absolute value of sine n times square root of n cubed over n cubed plus n plus 1 cubed. So what I did is I put these 2 together into one root. Now we have a problem. Does anyone see what the problem is? We could do this, okay? If we needed to, we could take that over here. We'd go n cubed. We could expand the bottom, become n cubed plus 3n squared. Ooh, squared plus 3n plus 1. So if you had some time, you could expand n plus 1 cubed out. You get this, and then you could run L'Hopital on that a few times. If you did L'Hopital, if you took this limit as n went to infinity, you get 1 there. So this whole piece would be going to the square root of 1, which goes to 1. Is that okay? Without showing all the work?
Yes, sir.
But this is a problem. Because as n goes to infinity, what does sine of n do? So think about what sine n does. It's just jumping up and down, right? This limit does not exist. And therefore, this limit comparison test is not going to work. Now, that does not mean that what we compared it to doesn't work. It just means that the limit comparison test doesn't work. So maybe we need to go back and we need to look at the blue version, which means that we just have to show that this inequality is true. So maybe we can show that this inequality is true. Maybe, right? So instead, I want to show, I'm going to do it up here. I want to show that A sub n is less than B sub n. It can be equal also, but it doesn't matter. Okay, so I want to show that absolute value of sine n over this is less than or equal to 1 over square root of n cubed. What do y'all think? How could we show that? Or do you believe it now? Do you believe it now? I mean, think about this. Which denominator is bigger? That one's bigger, right? Bigger denominator than this one. Which numerator is bigger? Which one? The one, right? This one should be bigger than the sine of n. Well, it could be equal, couldn't it? It could be equal, but so generally speaking, what we're saying is that our numerator over here is bigger, right? The numerator over here is bigger. And the denominator over here is smaller. So if you take a fraction, you make the numerator a little bit bigger and you make the denominator a little bit smaller, won't this side be bigger than that side? Yeah, so this is true. Now we can maybe do some algebra, but just by inspection, I can see that this inequality is going to hold. Trying to think of another way. We could have cross multiplied. If you cross multiply, you get this. Maybe it'll make more sense this way. Like that. So if you did the like cross multiplication, then maybe you can tell that like this number here, the biggest it could ever be is 1. So it's either less than or equal to 1. And then this right here is some number, right? And when you compare that, this number to this one, this number, right, is bigger, isn't it? This number is bigger than that one. So this number is bigger. And then you can imagine there's a 1 next to it, which is bigger than or equal to this. It's the same argument, really. The right side here is bigger than the left side. Okay, so we're done. What we can say now is that since this inequality held, right, since that inequality held, what we know is that this series converges, right? This series converges. That means that this one is absolutely convergent, and by the theorem, that means that that's convergent. So I hope you can follow all of that. Therefore, this series, the original one, converges. Showing series converge is, in general, it's difficult, right? I mean, there's just a lot of things you have to pay attention to, and you know, here we're going to try and use a theorem, but then when we get to this, we say, oh crap, now we got to compare it to something. We compare it, we try limit comparison, didn't work, so we inequality, oh that worked, and then we draw our conclusions. So there's lots of different roads you can go down, right? It's not just a straight path every time. Okay, let's look at a very interesting one. Okay, is this series absolutely convergent? Now, didn't we start, when we started today, we started talking about alternating series? Isn't that the first example I gave you? Yes. That is right, -1 to the n over n. So we already know, does that series converge? Does this converge? We already did the work for it. Does it? Does, right? This converges, but I'm putting in red because we're going to act like we don't know that, right? So do you think that the absolute value converges then? Seems like it might, right? It should, but look, if you take the absolute value of this, then the -1 doesn't matter, right? It just becomes a 1, and on the bottom you get n. And what does that series do? What type of series is that? It's harmonic. That diverges. Wait a minute, hold on. This diverges, but that converges, right? The theorem said what? What did our theorem say? The theorem said that if the absolute value converges, then the original series without the absolute value converges, right? That's what the theorem says. If the absolute value converges, then it's guaranteed that the original series converges. This theorem does not say that if the absolute value diverges, that the original series must diverge. That's not what the theorem says. So this is perfectly fine. If the absolute value diverges, then you know nothing about the original series, right? It could converge, it could diverge. It just depends. In this case, the original series converges, but we'd have to show that with the alternating series test. So this is just a good example where you have to be careful with the absolute value, because if you look at the absolute value and if you're always focused on whatever happens here, then you're going to be wrong. It's only if you have convergence that you can conclude you have convergence there. And this brings me to a comment that I want to make about logic, okay? This right here, this theorem is called an if-then statement. And those of you who have not taken a logic course, which a lot of you probably have not done logic, but enough of you are computer science majors that I know that logic is going to become something you have to understand pretty deeply. In our logic system, this statement up here is set up like this: if P, then Q. If I can give you an example of this, of an if-then statement that'll make a little more sense. If you, do you agree with this? If you live in Texas, so let's say you're actually physically in Texas right now, okay? If you're in Texas, then are you in the United States of America? Is that true? If you're in Texas right now, then you're in the United States, at least until Texas secedes from the Union and we become our own. At least for now, this is a true statement, right? Does that statement work the other way around? Are you free to just flip the order of things? So if you're in US, then you're in Texas. Well, no, you could be in New York, right? Which means you'd be in the United States, but you're not in Texas. So when it comes to if-then statements, you are not free to just flip them around. So in this statement here, if the absolute value converges, then the original series converges. You cannot say that if the original series converges, then the absolute value converges. You can't reverse the direction. Now, sometimes in math, you can. Sometimes you can go both directions, all right? And let me get to that in a second. Yeah, I'll say it now. So anytime you have an if-then statement that does this, where it's if P, then Q, and it works the other way, if Q, then P, then most of the times what we do in math is we write this, P, I, F, Q. And this means P if and only if Q. And this basically can be read both ways. You can go, if P then Q, and then if Q then P. And that's the way we distinguish it. Another way we do it is this. I'm just showing you some notation. If you write this statement right here, this statement right here can be written P implies Q. And then this statement can be written Q implies, the double struck arrow means implies, Q implies P. So if you see P implies Q, it means if P then Q. If you see Q implies P, it's if Q then P. If I want to say this, another way to say it would be to do a double implication, arrows in both directions. So it's if P then Q and if Q then P. This is a very strong statement. This right here is a very strong statement. Let me give you an example of an if and only if. So if X is an element of the real numbers and X equals 2, then um, 3X equals 6. Do y'all agree that that can be rewritten the other way? In other words, if 3X equals 6, then X is a real number and X equals 2. Do y'all agree that both of these statements are true? If you give me a real number, let's say it's 2, then if I do 3 times 2, I'm going to get 6. On the other hand, if I tell you that 3 times the number is 6, then the solution to this is X equals 2, right? So that means that X is a real number and X is 2.
Right.
So another way I could write this is you don't see that? Or you could replace, sorry, my double arrow is so sloppy. That's the math person in me. I just, yeah. You could also replace that with if and only if you wanted to. One more. I'm just having fun now. So what about this one? You tell me whether or not this is right. X is real. X is 2. If and only if X squared is 4. Do you think that's right?
Yes.
So if X is a real number and X is 2, do you agree that X squared must be 4? Yes? And the other way works also?
No.
If X squared is 4, then is this true? I'm sorry, if you said something, Alex, I didn't hear you.
No, he said that the other way.
So from left to right, we all agree that's true?
Yes.
Okay, from right to left, is it true?
Yes, also not true.
If I take a number and square it and get 4, then does that mean that the number I squared was 2?
Yes.
It could be.
Yeah.
Are there any other numbers that it could have been? How about -2?
Yeah, -2 could work. Yeah.
Could have been -2, couldn't it?
Mm-hmm.
Yeah, so that implication the other way doesn't work, which means you can't do a double arrow. You can only do the arrow in that direction. Does that make sense?
Makes sense.
So my whole thing here is you have to be very careful with statements like if P then Q. You can't flip them around. You're not allowed to. Now there is something you can do. I'm getting way too into logic. Has anyone done any logic if P then Q?
No,
There is.
I don't know.
There is an equivalent statement to if P then Q. So if P then Q, I said another way we could write that is P implies Q. An equivalent statement to that is this. If not Q, then not P. And this is what's known in logic as the contrapositive. So a lot of times, if you ever get into having to prove things, if you're trying to show that this is true, if you're questioning, is this true? then if you can show this is true, then it's equivalent to showing that's true. I'll give you an example. If you're in Texas, then you're in the US, right? If I was having trouble showing whether or not this was true, then here's what I could try and show. If you're not in the US, then you're not in Texas. So maybe it's easier for me to show this. If I can show this, then that one is automatically proven. Okay, but this gets into things called truth tables and equivalence and all this stuff we're not going to get into here. But there is one more thing, I apologize, one more thing. There's something really crazy in our logic system, all right? First, we have what's called the law of the excluded middle, which means that given a mathematical statement or given a statement, a logical statement, it can either be true or false. It cannot be true and false at the same time. So the law of the excluded middle means that you have true and you have false and you have no other options, okay? There's no middle, okay? So we have the law of the excluded middle. So with that law of the excluded middle, we have some really strange things that you can actually have happen. So watch this. Watch this statement. If x squared, okay, let me do it this way. If x is a real number and x squared equals -4, then x is 7. My question is this true? So we have a mathematical statement. It's either true or false. There's no middle ground, okay? So is that a true statement or a false statement? If x is a real number, okay? So we're saying x is a real number and x squared equals -4. Then my conclusion is that x is 7. True or false?
False.
What do you think? What's that?
False.
Seems false, right? Why does it seem false?
Well, 1x squared can't be a negative number.
X squared can't be -4, as long as we're talking about real numbers. Now, if we're talking about imaginary numbers, complex numbers, it is possible. But if x is a real number and I tell you that x squared is equal to -4, then x is 7. What? This statement is actually true. What? And the reason why it's true is because your assumption, right? The assumption is false. And anytime you start with a false assumption, the conclusion is always true. That's a strange thing about our logic system, but it's the way it works. I'll give you another example. All of the pink elephants in my jail cell here, see I'm in jail, all the pink elephants in this jail cell with me today have wings. Have wings. That's true. That's a true statement. And the reason why is because in order for you to prove it wrong, you would have to find a pink elephant in this jail cell with me that does not have wings. See, my assumption is false. And anytime you have a false assumption, your conclusion is always true. It's a strange thing about our logic system, but it's the way it works. So we have a special category for things like this. We actually say that this is vacuously true. I'm going to misspell it. Vacuously true. It's like, yes, it's true, but it's true because your assumption's false. And those aren't interesting to us at all, but they're part of our logical structure. We have to have it. There's another one that I like to throw out there. Just this is more of a thought exercise. So I'll give an example. I'm going to use one of you because it'll be easier for us to make sense out of it, I think. And I promise this is my last thing, then I'm moving on. Okay, so Coleman, right? Coleman, one of your classmates here. Coleman, listen to the statement carefully. Coleman cuts the hair of everybody in San Antonio who doesn't cut their own hair. All right, I'll say it again. Coleman cuts the hair of everybody in San Antonio that doesn't cut their own hair. And we're assuming Coleman lives in San Antonio. I don't know if Coleman does, but Coleman cuts the hair of everybody in San Antonio who does not cut their own hair. So the question is, who cuts Coleman's hair?
Maybe Coleman cuts his own hair.
Okay, so if Coleman cuts his own hair, then wouldn't Coleman be cutting the hair of somebody who does cut their own hair? But I just said Coleman cuts the hair of everybody who does not cut their own hair. So it can't be Coleman, right? So could it be someone else? Well, if someone else cuts Coleman's hair, then there's somebody out there cutting people's hair in San Antonio that don't cut their own hair. But Coleman is the only one who's supposed to cut the hair of people in San Antonio who don't cut their own hair. So Coleman's hair, I guess, is never going to get cut. I don't know. It's one of those weird logic puzzle things. There's no correct answer, okay? Because but it's like vacuously true. It's impossible. It's an impossible scenario. Okay. Yeah, so pure mathematicians, anyone who's actually going to take some pure math classes, you get into logic, you get into things like that, and you start to really explore these really strange things. And even computer science, when you get to a certain point in computer science, usually the graduate level in computer science, math and computer science almost become very much the same thing. It's all about logic. So, all right, we're moving on. Thank you for allowing me to go off on a tangent there. Okay. Very good. Now, the almighty ratio test. I'm going to give it some stars. I'm going to give it some happy faces, some balloons. Okay. We love the ratio test. This thing is we're going to use this so much now for the rest of this chapter, this ratio test. Here's what it says. If you're given, or let's just say given a series, okay? Given a series. If the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n that did not come out right. A sub n plus 1 over a sub n is less than 1, then the original series converges. That's it. That's the ratio test. So they call it the ratio test because you're going to be taking the limit of a ratio. And look at the ratio. You're doing the original sequence, the n plus 1 term of it divided by the n term of it. So it's like you're looking at the nth one right after it, and you're taking their ratio, and you're figuring out whether or not that ratio is going to something less than 1. If it does go to less than 1, then the series converges. Now, if, I should have put here if in front of that, sorry. If this limit is less than 1, then it converges. Now, if that limit what do you think? If the limit is greater than 1? You would think, oh, it's probably going to fail, right? The test is going to fail. I'm going to try something else. Nope. This test is badass. Then the series diverges. Okay. So it's like the ultimate awesome test, because when you run the test, if it's less than 1, you've got convergence. And if it's bigger than 1, you've got divergence, which is awesome. The only problem we run into is if it is 1. If this ratio test yields the number 1, exactly the number 1, then the test fails. But there's only one value for which it fails, okay? And that's 1. Let's take a look at this test on our formula sheet.
Can I ask you a question, sir, about the ratio test?
Yep.
What if you get 0?
0 less than 1?
Well, we have less than 1, greater than 1, and equals to 1, but what about 0?
0 is okay. 0 is
Where-
less than 1, right?
Oh, yeah, you are right. I'm sorry. I was thinking only
No,
negative
it's okay.
numbers for some reason.
Now, here's the thing, though. The smallest it could ever be would be 0, because you're taking the limit of the absolute value, right? And since you're doing an absolute value, the worst that could ever happen is that you get 0, right? But you're never going to get a negative number. All right, so let's look on our formula sheet. Here it is, the almighty ratio test. The thing that's so great about this test, there's no restriction on the series. It can be alternating. It can be like the one we just did with the sine n over whatever. It can be any series. There's no restriction. You know, with the comparison test, we have to have that the sequences here have to be positive. So the ratio, there's no restriction. Excuse me, I'm sorry. If we take this limit, we get some answer L. If L is less than 1, look, not only does it converges absolutely, okay? Which means that's even stronger than regular convergence, because if you have absolute convergence, it implies convergence, right? And then if L is bigger than 1 or even infinity, then we get divergence. And then it says it's inconclusive if L is 1. It's useful if we have factorials. Ratio test is great for problems that have factorials in them. And yeah, all right, so let's do it. Let's do an example. Okay, first one we've got here. Let's do sum n equals 1 to infinity, -1 to the n times n squared over 4 to the n. So we're at that point in the class where we pretty much have almost the entire formula sheet. There's still another test or two, but those are actually pretty trivial. Okay, we don't use them very often, and you'll know when to use them because there's a certain thing that has to look a certain way. But at this point, we have everything. Everything's on the table. So this is where it becomes challenging to figure out what to do, right? So you look at this and you're like, okay, it's an alternating series. So maybe I want to do the alternating series test, right? It's kind of geometric because you have 4 to the n, but then you've got this n squared, so that makes it not geometric. So you know what? Let's just go with the ratio. Let's just do the ratio. So I'm going to take the limit as n goes to infinity of the absolute value. And now what I have is a ratio. So I've got to take this thing, replacing all the n's with n plus 1s. And then divide that by the original sequence with just the n's. Everyone see the ratio there? All right. Now, here's the first thing I'm gonna do. I'm gonna totally ignore the -1s to the n's. Just gonna throw them away. Because again, no matter what, those are gonna become positive ones once I do an absolute value. So I'm not even gonna consider them. Is that all right? Now on the top, let's see, I'm gonna watch the way I write this. I'm gonna do n plus 1 squared over, watch this, 4 to the n times 4, and then times 4 to the n over n squared. So what I did here was I rewrote this 4 to the n plus 1 as 4 to the n times 4. And then the fraction on the bottom, I flipped it and brought it up to the side. Do y'all see that? This is just algebra here. Any questions? Do y'all see why I split this 4 to the n plus 1 up? Do y'all see that goes away? Okay, so this is limit n goes to infinity, absolute value. All right, what do I have here? On the top, I have n squared or n plus 1 squared. And on the bottom, I have a 4n squared. And I'm going to expand the numerator. Right, if I FOIL that out. And that's infinity over infinity, right? So L'Hopital. If you do L'Hopital, I'm not going to show the work, you should get 1/4. And that's less than 1. And so the conclusion is that this original series up here converges. Okay, you ready for another one? Here we go.
Can I have a little bit more time to write this down?
Yeah, take your time. I'll put the next one down here and let you all start. I want you all to start trying this one on your own. It's n factorial over n to the n. So why don't we do our little Jeopardy here? I'm going to give you 3 minutes to see how far you can get with this. And do the ratio test, okay? Do the ratio test and see how far you can get. Okay, let's talk about this. Were you all able to get up to this part at least? This is a sub n plus 1 over a sub n. So just be careful. Every n gets replaced with n plus 1, even the base and the exponent here. Then over this, the next step, all I did was flip this one up. Anyone have an idea of how I can handle some of this?
I kind of did something, but I'm not too sure if it's right.
Okay.
Earlier when we were going over sequences with n plus 1 factorial and n factorial, most of it kind of cancels out, right? Like
That's
n plus 1 factorial goes down to n, then n minus 1, and so does n. So aren't you just left with n plus 1 at the end of all that cancellation?
Exactly. Yep, exactly. We had this when we were covering factorials, and this is, we're going to use that a lot. But that's true. Oh, wait, that cancels. Sorry, n plus 1. Good. So what we would do is we'd rewrite this n plus 1 factorial as n plus 1 times n factorial, and then cancel the n factorials. All right, that's good. Now let's see what we have left then. Okay, I have an n plus 1 here on the bottom. Couldn't I rewrite the bottom as n plus 1 to the n times another n plus 1? And then times n to the n like that? Isn't that what n plus 1 to the n plus 1 means? It's n plus 1 to the n times n plus 1? Because these both have the same base. So if you put these together, you just add the exponents, n plus 1, you get that. Do you all agree? Okay. Now, do you see that this cancels? Right? So we got limit n goes to infinity, absolute value. Okay, we've got n to the n on top, and we've got n plus 1 to the n on the bottom. Now, since they're both raised to the n, I can do n over n plus 1 to the n, like that. Crap. Okay, so this isn't good, because if we look at what's happening here, any questions up to that point? Okay, this right here, if we do the limit, it's L'Hopital, that goes to 1, right? It's never going to be 1, but it's headed to 1. And then the exponent is headed to infinity. And 1 to the infinity is an indeterminate form from Cal 1. We don't know what that's going to. Okay, we don't know. So we have to do some work. So this is a good spot for me to say, all right, I better figure out what that is. I need to figure out what the limit as n goes to infinity of n plus 1, or I'm sorry, n over n plus 1 to the n is. Does anyone remember how to deal with an indeterminate form where you have 1 to the infinity? No? I think we may have done only one example in this class. So let me run through this. This is how I do it, all right? This is how I tell my Calculus 1 students to do it. I'm gonna have to do this on another page. Okay, so what I tell my students is anytime you see 1 to the infinity, there's a couple of other forms that you could have like this. You could have 0 to the 0, that's an indeterminate form. Infinity to the 0. I feel like I'm missing one. What am I missing? Well, those are 3 of them. I think there's only going to be one more.
Infinity over infinity.
Yes, but those are, yes, infinity over infinity is an indeterminate, 0 over 0 is indeterminate, infinity minus infinity is indeterminate. All of these are. I'm just saying for the ones that involve powers, those are the ones that involve powers. And anytime you see one of those 3, what you do, or what I tell my calculus students to do, is just to call this limit y. Just call it something. And then what we do is we bring the natural log in on both sides. And what the natural log does is it allows me to put the natural log in front of this expression. And then properties of logs allows me to take that n and drop it out front. So what we get is the natural log of y equals the limit as n goes to infinity of n times natural log of n over n plus 1. And now you have another type of indeterminate form. As n goes to infinity, you get infinity times that goes to 1, but then natural log of 1 is 0. So you get an indeterminate form of infinity times 0. That's another type. So this is going to infinity. This whole thing with the natural log is going to 0. And so does anyone remember how to deal with that form? Never knew L'Hopital would become so useful. See if this rings a bell. If you have this form, infinity times 0, you pick one of the two and you drop it to the denominator. So I'm going to take the n, I'm going to leave the natural log up here, but then I'm going to rewrite the n out front as a 1 over n on the bottom. So this is the same, algebraically, this expression is the same as this expression. Because if I put a 1 over n on the bottom, I could flip that back up and put it in front. So I'm just rewriting it this way, because now if I look at it, this numerator, the whole thing goes to 0, and this denominator is fixed over infinity, that goes to 0. Now you have 0 over 0. And 0 over 0 is an indeterminate form, but that's when we can do L'Hopital, right? So the whole idea behind this is if you have one of these forms, you do natural log to pop the exponent out front. That will give you a product that's an indeterminate. You drop one of those down, now you have 0 over 0. You could have infinity over infinity, it just depends on the problem. But at this point, we're going to bring in L'Hopital. So I bring in L'Hopital. Here's L'Hopital. And that means derivative of the top and the bottom separately. Okay, derivative of the top. The derivative of natural log of something is 1 over that something times, crap, the derivative of what's in here. The derivative of what's in there. Chain rule, right? So I have to do quotient rule on that. So that's the derivative of the top times the bottom minus derivative of the bottom, which is 1 times the top all over the bottom squared. Okay, so that's the derivative of the top right there. Then I take derivative of the bottom, which is just negative 1 over n squared. And now I try and clean that up. That's equal to limit. They don't all get this ugly, but what does this turn into? What does all this right here turn into? N plus 1 minus n. So isn't that just 1 on top? 1 over n plus 1 squared. All over negative 1 over n squared. One of the n plus 1s cancel. And I'm going to go ahead and bring this guy on the bottom. I'm going to bring him up top, make it n squared over negative 1 like that. And one of these n's cancel. I know I'm doing a lot of steps, but this is just algebra. So hopefully you can resolve this. What am I left with? What's on top? Is that just n up there? I feel like I've lost y'all. Are y'all okay?
Is it negative n over n plus 1?
Yeah, you can bring that negative there up top. That's fine. Negative n over n plus 1, fine with me. Okay. Now remember, this is natural log of y, right? Natural log of y equals this. Now when we do that limit, we get infinity over infinity. We do L'Hopital 1 time, and we should get negative 1. Now, what were we trying to find? We were trying to find out what y was, right? We wanted to know what y was, this original limit. And what we have is that natural log of y equals -1. So we need to get rid of the natural log now. So we do the exponential on both sides here. The e and natural log kill each other off, and you get e to the -1, which is the same as 1 over e. And I hope that you would agree that that is less than 1. 1 over e is less than 1. E is about 2.718. So, yeah. Okay, we're there. We have concluded here that when we do this limit, right, all this stuff, we were stuck right here. We know that that's going to be equal to 1 over e, which is less than 1. Therefore, what does this series do? Converges. Right, converges. Okay. We have more to do next class. I have 4 minutes, so I'm probably going to take more than 4 minutes to do this. So if you need to leave, that's fine. This is that thing I had started talking about last class. If you're interested, if everyone leaves, I'll just close the session out. So, excuse me. All right, homework for tonight. Let me just say, for homework, do as much as you can for 8-4, all right? Follow my homework solution videos. If you are doing the homework and you hear me say root test, we have not done the root test, okay? So just skip that problem, all right? All right, so here's the thing that I was talking about next class or last class. And again, if you don't want, I'm going to start over with it. So if we have 1 minus 1 plus 1 minus 1 plus 1, if we do this, I could call this sum S. And then if I write S again, but I rewrite it with a 0 in front, it's the same thing. And when we add those straight down, you would get 2S here. And then everything would cancel except that 1 out front. So you get 1 here, and that would mean S is a half. Okay, I kind of ran through something like that last time. So now what I'd like for you to consider is this. What if I call T equal to this sum, 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 minus 8. Do you think this converges or diverges? Well, I mean, you could have an opinion, but let me do something, all right? I'm going to write T down again. But again, I'm going to shift it to the right one. Y'all following me? Add straight down. What would happen if you add straight down? T plus T is 2T, right? And then what do you get here? 1, right? What about here?
-1.
Minus 1, then plus 1, then minus 1, then plus 1, then minus 1, then plus 1, then minus 1, plus ... right? But isn't that S? Isn't that this? And what do we say S is? A half, right? That's a half. So 2T would then have to be equal to a half. So then what would T be equal to?
S.
No, just take this out. So this right here, this all that adds up to be a half. We just showed that here. But that would mean algebraically that if I divide both sides by 2, I would just get t as a fourth, right? This should be mind-boggling at this point, right? If I take 1 and subtract 2, then add 3 and subtract 4, and then add 5 and subtract 6, what I'm saying is that this sum right here adds up to be what? A fourth. What the hell is going on here, right? Does this seem very strange? Well, check this out. New one. Let's do, this is the last one. Let's call this one, I don't even know what to call it. I'll just call it T. I'll call it E. 1 plus 2 plus 3 plus 4 forever. Now, there's no way that that series converges, right? If I just take 1, then add 2, then 3, then 4, and just do that forever, that thing's going to blow up and become infinite, right? Yeah? Yeah. Okay, so now what I'd like for us to do is look at, hold on, I always forget what my next step is here. I haven't done this in a while. Where was it? Yeah, so I'm going to subtract it. Okay, so now what I'd like to do is I'd like to write down now, or I'd like to take this E, and from it, I want to subtract T. Okay, so let's subtract T. That means I'm going to subtract from this. Remember what T was? Here was T. So I'm going to subtract that. So I'm going to subtract 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 dot 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 forever. Okay, let's go ahead and figure out what this is. So the left side of this is E take away T. The right side of this is, let's do it. What would happen here? If I do 1 and then I take away 1, what would I get? 1 and then take away 1.
0.
0, okay, I get 0. And now I'm going to do 2 and take away negative 2.
4.
4. And then I'm going to do 3 and take away 3.
0.
0. Next one, I'm going to do 4 and take away negative 4.
8.
8. We'll do maybe one more. Next one will be 0, right? 5 take away 5. And then the next one should be what? 6 take away negative 6?
12.
So 12 and then plus 0 and then blah, blah, blah. Right, the next one should be what? 16, right? Okay, so this is really E take away T is really 4 plus 8 plus 12 plus 16 plus dot, dot, dot. And check this out. I can factor a 4 out of each of those. Can't I? All of these have 4. Now, do you recognize this? 1 plus 2 plus 3 plus 4 forever?
It's E.
That's E, right? That's E, right? That's E. That's what we're trying to find the sum of. So I'm going to rewrite it this way. E minus T must be 4 times E, right? All right. Okay, what can we do? Subtract E on both sides. Negative T equals 4E, take away an E, you got 3E. But wait a minute, what was T? Didn't we figure out a number for T? T was 1/4. So we're saying negative 1/4 equals 3 times E. And now if we divide both sides by 3, we get negative 1/12 equals E. Which means that 1 plus 2 plus 3 plus 4 forever equals negative 1/12. That should blow your mind, right? It doesn't make any sense. Now, this is actually pretty cool because algebraically, this all makes sense, right? This all makes sense. But here's the problem with it. I made a huge mistake at the beginning. I said that this sum was equal to something. And that's not okay because that sum is divergent. That's a divergent series. And if a series diverges, that means we can't say that it sums to something. Here's the way I can maybe help you remember this or think about this. Do you remember when I told you this? If you have two series together, two sequences together in a series, that you're allowed to split it up into two. Do you remember that? You're allowed to split into only if what though? If these two things converged, okay? If these two converged, then the algebra of splitting them up is allowed. Well, it turns out that when you're looking at series, if they converge, you can rearrange things. You can change the order, you can shift things around. But if they diverge, you can't. So this is a way you can show this to someone and just like trip them out, you know, like make them be like, what the hell's going on here? Because it all looks legit. But you can't call this thing T. You're not allowed to, because this is not a fixed number. This is not converging to anything. But if you set it up this way, you can make someone believe algebraically that 1 + 2 + 3 + 4 forever is -112. Anyway, okay, I just thought that was an interesting thing to show you all. I will see you on Wednesday. We'll wrap things up here for the week, and hopefully we'll start 8.5. We really need to get into power series. We will start 8.5, in fact. Okay. Have a good one, everyone.
You too. Thank you.
So, Professor,
Yes.
you know how you said like you made a mistake in the beginning? Does that mean everything else was inconclusive because of that?
That means that I can't do the algebra that I did here. Like, I'm not allowed to take S and add it to itself and get 2S. Like, that's not legitimate, because this sum is not S. It's not I'm assuming here that S is a finite number, right? That S is like numerically finite. So adding S together with S would become 2S, which algebraically it does. But when we say that S plus S is 2S, we are assuming that S is a real number, right? But it's not. S is not a real number here. Same with this second one, when I call this sum T, right? And I add them together. Of course, T plus T is 2T, but T has to be a fixed number for that to work. It can't be, T is not, this series diverges. This series diverges. So as soon as we know it diverges, we can't say it adds up to be a number T. But if people don't know that, they don't focus on that, then they're like, okay, yeah, that all makes sense, right?
Sure. Well, thank you, Professor.
Yeah, no problem.
Have a great day.
You too. Varun, do you have any questions? You're on mute.
Sorry about that. I had no idea. I had a question regarding grades.
Yeah.
Do you know when the final grade, or when grades are going to be finalized for the course by any chance?
So usually, let me see the calendar. Our final is on December 7th, right? Okay, so our final's on December 7th, which is 2 weeks from today. Oh my God.
Oh, dang.
That's crazy.
That's coming up. I didn't even realize that.
Okay. So the grades, this is finals week. And so the grades will be due that following Monday, which would be the 14th. So I have a deadline of 5 p.m. Now, here's the thing. I will post the grades in Canvas for you. You'll see what your grade's going to be. But then I submit those. And it doesn't matter if I submit them on Friday or if I do Saturday, Sunday, or Monday. Monday's the cutoff date. And then it takes a while to process those to show up on your transcript.
Right.
Is that what you're concerned about?
Yes, sir. So I was actually trying to transfer to UTSA, and they wanted my final transcripts, and they said the cutoff for that is November 15th. So I was just gonna ask my professors. Oh, sorry, yeah, December 15th. My bad.
Huh. Well, you'll have to talk to them, because I think UTSA started a week before us, maybe. I think that's why everything is off. I don't know.
Oh, maybe so.
But I would talk to them about getting an unofficial transcript, or if there's something you could get each of your professors to write an email.
Yeah, I meant they did mention that I could take like a screenshot of Canvas,
Mhm.
and the only thing that I was like wondering about that was if they were gonna bring up whether it was doctored or not or in any way. And so they said that I can do that for right now, and then once the grades are finalized, if I could send that over, then I could probably go through it with that route.
Yeah, if you need an email from me, I can do something at the end.
I appreciate it. Thank you.
But that's something that it's not going to be just you, right? Everyone
Yeah.
at NVC is going to be in the same boat. If that's a hard deadline of the 15th, that makes no sense when our grades are due on the 14th. There's no way that people are going to have transcripts.
Yeah, it's
you know.
really hard to meet with that.
Yeah.
That's why I was wondering if I should stay after class and ask if there was a way that I could get it, like maybe see if there's a way I can get it like finalized earlier, or see if I could submit earlier. I don't think it's possible, right? You have too many
Nothing
exams to grade.
There's nothing I'm going to be able to do, because
Yeah.
that's all administrative and that's a process. And like, they're going to have every student at NBC that they have to process, right? So they're not going to be like, oh, this student and this student, let's get those early, because they do it all like in a batch report. They don't do it like individually. So
It is quite odd they picked that date. I was thinking it'd be closer towards like winter break.
yeah, I will, let me contact the chair of our department and see if she's heard anything about like UTSA extending that or anything about that. You're sure that they said the 15th?
I was on a phone call with them, and they did say that like in order for, because I'm trying to see if I can get in by spring semester, and the one of the admissions people did tell me that I need to have, because like the cutoff for getting the final transcripts is the 15th. They
Yeah.
said that like you can do something temporarily where you can do like a screenshot
Yeah.
or something, or maybe even what you were saying, get an email and have them send that. But they told me that they would need to get the final transcripts by the 15th.
Yeah, that's probably what you're gonna have to do, is screenshots or emails.
Okay.
Yeah.
I appreciate it, sir. Thank you.
Okay. All right. Have a good day.
You too. Enjoy your Thanksgiving.
All right. You too. Well, if I don't see you Wednesday.
Oh, yeah, true. I'll still try and show up to class on Wednesday,
Yeah.
but I don't know. My English class isn't meeting up on Wednesday, so we were already saying Happy Thanksgiving.
I understand. Do what you gotta do. I have to be here. I can't cancel class. So.
No worries. I'll look forward to seeing you. Bye. Have a good one.
All right. Bye.